Hi everyone, Dr. P here, and in this lecture video we're going to take a look at types of reactions and how to identify them. And the first thing that we need to do is we need to look at different levels and as before we'll look at the molecular level and then we'll also look at the macroscopic level. So on the molecular level we've seen single replacement reactions, which is where we have AB plus C going to AC plus B. And we've also seen double replacement, which would be AB plus CD going to AD plus CB. And if we look at examples of these, we could see something like a single displacement might be, let's say, 2 HCl aqueous plus zinc solid react to give zinc chloride aqueous plus H2 gas. That could be one example. An example for a double replacement could be something like, let's see, let's do HCl aqueous plus NaOH aqueous. And like we've talked about in lab, we'll swap. I'm going to swap my H and my Na, and I will get NaCl aqueous plus HOH, which is simply H2O, and that's a liquid. Excuse me. There are other reactions that we could have. We've seen some already, some precipitation reactions or double replacement reactions. Now there are some other reactions that we're not going to run into as much in Chem 1A, but you will run into them in Chem 12A and Chem 12B. And these include things like addition reactions, where we have A plus BC reacts to give ABC. Elimination reactions, where let's say we have ABC reacts to give AB plus C, so we're eliminating C. We can have substitution reactions, which are actually the general term for single and double replacement reactions. Sometimes these are called displacement reactions instead, or substitution. So we're basically, replacing B with C, or we're displacing B with C, or substituting C for B. And then another kind that we could have is a rearrangement. Where we have A, B, C, and it undergoes some reaction to give us ACB, where the order in which our atoms are connected has changed. So the molecule has rearranged. Okay. Let's see if there's anything else on the molecular level. I don't think so. Again, our focus here is going to be on the single and double replacement reactions. So really it's 12A and 12B when we will get into addition, elimination, and rearrangement reactions. So that's at the molecular level. Let's take a look at the macroscopic level now. So we've already seen some of these types of reactions. One is a gas forming reaction. And typical gases that can be formed include H2, we could get O2, CO2 is a typical gas that's formed. Sometimes we could get other gases, we could get N2 gas, could get a halogen, Cl2 for example, but these would probably be the most common in terms of gases formed. Now, what's a typical example? Well, we already looked at one, which was 2HCl aqueous plus solid zinc gives us zinc chloride, ZnCl2 aqueous, plus H2 gas. So here it's the H2 gas that's given off that makes this a gas-forming reaction. Now there's another type of reaction that this is, and that's called an oxidation reduction reaction. I'll talk a little bit more about those later. But reactions can be more than one type. So you could have something that was gas-forming and also get a precipitate. And of course you have whatever the reaction type is on the molecular level, and then a reaction type on the macroscopic level. And those, of course, are going to have different terminologies. We could have precipitation, where some kind of solid is formed, and this is where you need to be familiar with your solubility chart, although I will give it to you on the exam. So an example here might be FeCl3 aqueous plus 3 NaOH aqueous react to give FeOH 3 times solid plus 3 NaCl aqueous. So here our iron 3 hydroxide is going to be our precipitate. It comes crashing out of solution. And then we can have acid-base reactions. And these can be in a variety of forms. So if we have at least one of the species is a strong species, we will get a neutralization. So we could have HCl aqueous plus NaOH aqueous react to give H2O liquid plus NaCl aqueous. And this is a strong acid and a strong base. I'll just abbreviate those SA and SB. We could have a strong acid and a weak base. And it still is going to be a neutralization, and we will end up with NH4Cl aqueous. And lastly, we could have something like acetic acid, which is a weak acid. That's aqueous, plus NaOH, aqueous, reacts to give us NaC2H3O2, aqueous, plus H2O, liquid. Notice that in an acid-base neutralization, you'll get some kind of salt all the time. And if you have a strong base, sodium hydroxide here is our strong base, you'll also end up getting water as well. What if you had a weak acid and a weak base? Well, let's look at that as well. So HC2H3O2, aqueous. So that's our weak base, our weak acid. And then NH3 is our weak base. And we will end up with NH4C2H3O2, aqueous. So again, we get a salt. So in the presence of a weak base, all that we get is a salt. But in all of these cases, we are neutralizing our acid with our base. And we end up with a solution that does not have a strong acid or a strong base in it. That's a neutralization reaction. Now there is another type of reaction that we might see for acids and bases. And those involve weak acids going to strong acids. And you know, I totally misspoke there. Sorry, that should be strong acid to weak acid. And an example of this would be something like HCl, aqueous, plus NaC2H3O2, aqueous. And those react, and we'll do our double replacement, and we'll swap the hydrogen, the H plus and the Na plus. And I get NaCl, aqueous, plus HC2H3O2, aqueous. Get my acetic acid. So I've gone here from a strong acid to a weak acid. Similarly, we could go from a strong base to a weak base. And it would look something like the following. A strong base could be something like NaOH. It's a strong base. And then we will add NH4Cl, aqueous. And what happens is we're going to swap the Na and the NH4, and so we'll have NaCl, aqueous, plus, here's the thing, if we swap the NH4, we get something, let me do this in a different color here, I'll do it in green, we get NH4OH. Some people will actually write this out. This is ammonium hydroxide. And some people will write it out. What this really is it is NH3 plus H2O, or aqueous ammonia. So if we do a swap like this and we get NH4OH, you should think to yourself, oh yeah, that's actually going to be NH3 aqueous. I'll even write the plus H2O so it balances. And this is our weak base here is the ammonia. So we've got our strong base, and it's reacting with some salt to give us a weaker base. And this is another type of acid-base reaction. Now I should take a little bit of time to actually talk about some aspects of acid-base reactions. Namely, maybe just go over some definitions of acids and bases, because it's not really a complete discussion if we don't talk about acid-base definitions. Acid and base definitions. I realize I'm writing in blue. I want it to be writing in black. The most restrictive definitions we have are the Arrhenius definition. So an Arrhenius acid is something that increases hydrogen ion concentration in solution, in aqueous solution. And then an Arrhenius base is something that increases OH minus ion concentration in aqueous solution. I'll just abbreviate that AQ and SOLN. Now, some more general, so these are fairly specific. For example, something like ammonia it does slightly increase the hydroxide ion concentration in aqueous solution, but there are other things that can be acids or bases that fall outside of this definition. So a more useful definition is the Bronsted-Lowry definition. And so for a Bronsted-Lowry acid is a proton donor. What's a proton? A proton is a hydrogen ion. Think about it for a minute. A hydrogen atom has one proton in its nucleus and one electron. If you take the electron away, you get a hydrogen ion. Well, what was left after you took the electron away? Just the proton. So a proton is a hydrogen ion. So Bronsted-Lowry acid is a proton donor, and then a Bronsted-Lowry base is a proton acceptor. This actually allows us to look at acids and bases in systems where water is not the solvent, where we don't have water present. So, so those can be useful. Now, to go back to our reactions for just a minute here, there are some things to look for. Look for H plus and OH minus combining to form H2O. H2O, H2O. Oh, here's H2O there too. Look for salts forming as well. And usually these are soluble salts, but not always. And then also look for having a strong species on the product side and a weak species on the reactant side. So I have the strong acid, hydrochloric acid, on the reactant, and the weak acid, acetic acid, on the product. I have the strong base, sodium hydroxide, on the reactant, and the weak base, ammonia, on the product. Okay. Now, let's see what else I wanted to make sure I talk about. I'm not going to talk about oxidation reduction reactions other than to say that reactions in which one or more electrons are transferred are oxidation reduction reactions. So maybe I'll just write that here. Call those redox reactions. And these are reactions in which electrons are transferred. And an example might be 2 sodium solid plus Cl2 gas react to give 2 NaCl solid. So the sodium is giving up an electron. Each sodium is giving up one electron to a chlorine, and you end up with sodium chloride. So we'll look at balancing these reactions a little bit later. I will record a video, but it won't be on exam 1, so you're not going to need to worry about that at this point. But we will do some closer study right before spring break, I think, of oxidation reduction reactions. Now there is one more interesting reaction I just wanted to mention because it does come up in the, or it comes up in the experiment for the lab 4 worksheet. And that is the curious case of carbonic acid. So this is carbonic acid. It's a carbonate ion with 2 additional protons, and it tends to fall apart and give us H2O liquid plus CO2 gas. So this is something to be on the lookout for. If you form H2CO3, then it's going to fall apart and you're going to get H2O and CO2. What's an example of that? Well, let's take vinegar, HC2H3O2 aqueous, plus NaHCO3 aqueous. Let's make this solid actually, solid. So that's baking soda, sodium bicarbonate. I'll swap my hydrogen for my sodium and I'll get NaC2H3O2 aqueous plus H2CO3 aqueous. But this guy breaks apart into H2O liquid plus CO2 gas. So it's just something to be on the lookout for. Here we've got an acid-base neutralization. That also happens to be a gas-forming reaction. And I think that's a pretty good note to end on. Again, the last video dealing with redox reactions, I'll record at a later time. It's not going to be on the first exam's material, so you don't have to worry about that. All right, well, until next time, stay safe out there. Bye now.